Hello, math people, and welcome to a new unit on math and algebra. We successfully completed quadratics, and now we're going into systems of equations. So a system is a special construct. It's a way of modeling some mathematical relationships, and you run into a system of equations when you have two or more variables. You can model the situation as two or more equations. Those equations have to do with the same situation, and you can graph them on the same pair of axes. So it's basically when you've got more than one set of constraints or more than one relationship that you can model about one situation, and you have to problem solve those relationships at the same time. This is one of those mathematical constructs that I've actually used as an adult in problem-solving situations. So it is a very real-world algebraic situation. And we're going to start off pretty straightforward with just some shopping problems. They're situations that you may not have realized are systems of equations before, but they are. So in this first situation, there's a person named Diego. Diego bought some raisins and walnuts to make a trail mix. Raisins cost $4 a pound. And walnuts cost $8 a pound. And Diego spent $15 on both ingredients put together. So our first task is just to figure out if each pair of values could be a combination of raisins and walnuts that Diego bought. So pause the video for a moment, see if you can figure out which of these situations which of these number pairs matches the situation. Okay, and now you're probably back. So let's check your answers. If we bought 4 pounds of raisins and 2 pounds of walnuts, 4 pounds of raisins at $4 a pound is $16. 2 pounds of walnuts at $8 a pound is another $16. That is not $15, that is $32. So this pair of values does not match. That's no good. I'll put an X on it. 1 pound of raisins and 1.5 pounds of walnuts. 1 pound of raisins times $4 a pound is 4. And then 1.5 pounds of walnuts at $8 a pound is, let's see, 12. So if we put those together, ooh, it's close, but it is not 15. That is 16. So this one doesn't match. 2.25 pounds of raisins and 0.75 pounds of walnuts. I probably could figure this out in my head, but I'm going to pull out a calculator. So if I do 2.25 times 4, then I get 9. And if I do 0.75 times 8, I know what that is. That's 6, because it's 3/4 of 8. And so 9 plus 6 is 15. So this situation can match. This one is good. 3.5 pounds of raisins and 1 pound of walnuts. Let's just check that one. I don't think it works, but we'll see. So if I do 3.5 times 4, then I get 14. And then 1 pound of walnuts is $8. 14 plus 8 is not 15. That's 22. So this last one doesn't work. And in this type of situation, you're basically just solving a linear equation. You're checking to see if the solutions to the linear equation work. And we found 1 that works and 3 that don't. So let's go on to the next part of the document. I'm going to turn off the drawing tools and we'll scroll down. So in this situation, so same problem, Diego has some raisins and walnuts to make a trail mix. Raisins cost $4 a pound, walnuts cost $8 a pound, and Diego spent $15 on both ingredients. So in this one, we've got a table of values, but one of those values is blank all the way down. And so we're going to try to complete the table for the other ingredient given the amount of the first ingredient that we bought. So in the first situation here, if we bought 0 pounds of raisins, let's say we spent all of our money on walnuts. This is going to be a really awful trail mix, but it's Diego's trail mix. So at $8 a pound, if we want to get to 15 pounds, then what we would do is we'd do 15 divided by 8, and that would be 1.875 pounds of walnuts. Okay, if we bought 0.25 pounds of raisins, 0.25 times 4 is $1, so then we would have had $14 left to spend on walnuts. So I would do 14 divided by 8, and that would be 1.75 pounds of walnuts. And working our way on down. If we bought 1.375 pounds of walnuts, then we need to figure out how many raisins we're getting. So 1.375 times 8 would be $11 that we spent on walnuts. That gives us $4 left we would have spent on raisins. And at $4 a pound, that means we would have bought 1 solid pound of raisins. I'm going to let you work through the rest of this table and finish filling it out. And then when you're done filling it out, pause, and we're going to graph those values on a coordinate plane using Desmos. Okay, we're back. So you should have finished filling out the table in this way. And then the next prompt is to write an equation that represents this constraint. So as I noticed from our problem solving, what we would do is we'd take the number of pounds of raisins and multiply by 4, and take the number of pounds of walnuts and multiply times 8, and then you add those two together, and that gets to be $15. So these values we can plug into Desmos and make a little graph. So I'm going to pause and put the graph into Desmos, and then also graph this equation in Desmos so you can see how the equation fits those dots. And we're back. So here's that same relationship graphed in Desmos. So when you want to graph a table in Desmos, all you do is you just click this little plus, and then you'll choose table. And you can put in a table of values. So I just entered all of our values here for Diego's trail mix situation. And then the next line down, I typed in the equation that we came up with when we were describing Diego's situation. And if I turn that equation on, notice it doesn't need to be solved for y to graph in Desmos. You can type in the equation in standard form, and the line matches those points. So all these points are solutions to the equation 4x plus 8y equals 15. So if Diego spent $15 total, that line represents all the possible quantities of raisins and walnuts that he could have bought, all the possible number of pounds. Of course, in a real life situation, the negative numbers, both in the x and the y direction, wouldn't be valid numbers. So your domain and your range would be restricted to just the positive numbers in a real world situation. Okay, so going back to the document, it introduces another constraint on problem number 2. So in problem 2, here's a new piece of information. Diego bought a total of 2 pounds of raisins and walnuts combined. Now in this situation, we're going to forget what we know about the price of them and just focus on the total weight. So in this situation, if the raisins and walnuts together would add up to 2 pounds, we can fill in the table with that information. If we bought 0 pounds of raisins, that would mean we bought 2 whole pounds of walnuts. That's disgusting, but okay. If we bought 0.25 pounds of raisins, we would get 1.75 pounds of walnuts. If we bought 1.375 pounds of walnuts, I think that would be 0.625 pounds of raisins. This is 0.75. This is 0.25. And this situation is kind of nonsense, but we'll fill it in anyways. If he bought 3 pounds of raisins, he would have had to give away 1 pound of walnuts. Not really sure how that worked. So in this situation, this is a different equation. If we add up the number of pounds of raisins and the number of pounds of walnuts, then we get 2. So let's plug that table and that equation into Desmos, and you're going to see it makes a separate graph. Okay, so I've entered a second table, and then in this table, I put in the number of values that I could put in if the amount of raisins and the amount of walnuts adds up to 2 pounds total. And then the next line down, I wrote the equation for that same situation. And when I turn that equation on, you can see it lines up with those dots in a different straight line. So the black straight line represents the all the possible values that would add up to $15 if the raisins were $4 a pound and the walnuts are $8 a pound. And the purple line is all the possible values that you could get if you bought 2 total pounds. You'll notice there's only one place on this line that matches both situations. So this 0.25 and 1.75 represents the number of pounds of walnuts, or number of pounds of raisins, that's on the X, and the number of pounds of walnuts, that's on the Y, that you could get if you're going to meet both constraints. if they add up to £2 and the total cost adds up to $15. That's the nature of a systems of equation. We have two relationships, two sets of constraints. One of those relationships is 4x plus 8y equals 15. And it's a linear equation that matches the total price of the trail mix. And then in the next situation, your x plus y equals 2. Different equation, but same variables, can graph it on the same axis, and it has to do with a different relationship in this situation. This is the total weight of what you bought. And there's only one value that is on both lines at the same time in this situation. That is the solution to the system of equations. 0.25 and 1.75 is the only solution that matches both constraints at the same time. In the next part of the document, we're going to take a look at some other situations and try to figure out where the solutions to those are. So I'm going to clear our Desmos graphs here. So let's get rid of this stuff. Goodbye. Hopefully you entered that on your own. And then in the next couple situations, we're going to try to solve these by making tables or making graphs or whatever situation works for us. So in this situation, there's a dining hall. It has a total of 25 tables. Some are long rectangular tables and some are round ones. Long tables can seat 8 people and round tables can eat 6 people. On a busy evening, all 190 seats at the tables are occupied. So in this situation, we've got two constraints again. We have the total number of tables. They have to add up to 25. And we have the total number of seats at the tables that has to add up to 190. So we could write the equations first, and then we could make the tables or whatever makes sense. In the first equation, x plus y must equal 25. And you can just fill this table with as many values as you can think of that add to 25. We could have 0 long tables, and we could have 25 round tables. We could have 25 and 0. We could have 12 and 13. Right? We could have 20 and 5. So lots and lots of different combinations fill in the table. In the next one, we know that there's 190 seats total, and we know how many people can sit at round tables and long tables. And long tables are x, round tables are y. Therefore, 8 times x, so 8 people at each long table, plus 6 times y has to add up to 190. This one's a little bit harder to just like guess and check. But if you're kind of creative with it, you can think of some. So one possibility might be, let's say x is 5. 8 times 5 is 40. So then you have to ask yourself 6 times what would be the remaining 150. So let's do 150 divided by 6, and that would give you 25 round tables. Okay, so that's one combination that would seat you 190 people. And just go down the list and list other combinations that would work. Then we'll go to Desmos and we'll graph it. So pause there, we'll go to Desmos and we'll graph these two equations. Okay, I had to zoom out a little bit to see it, but I took our two equations and I plugged them into Desmos. X plus y equals 25, and 8x plus 6y equals 190. The black line is the total number of tables adding up to 25, and the red line is the total number of seats adding up to 190. And those lines represent all the possible values that would match each constraint. But as you can see, again, there's only one value that matches both of those constraints at the same time. And that's where you have 20 of the long tables and 5 of the round tables. So I know that 20 plus 5 add up to 25, so that works. And then if I do 8 times 20, that's 160. And 6 times 5, that's 30. 160 plus 30 is 190. So this is the one combination that meets both of those constraints. It's the solution to the system of equations. Okay? Next one down. So a family bought a total of 16 adult and child tickets to a magic show. Adult tickets are $10.50 and child tickets are $7.50, and the family paid a total of $141. So again, I see two situations and two sets of constraints here. The first is the total number of tickets. X plus Y must add up to 16. So we'll write that as one of our constraints. Okay, the next one is that the price of all the tickets must add up to 141. The adult tickets are X, they're $10.50 each, so $10.50 times X plus $7.50 times Y must equal 141. And I'll challenge you first to try to fill in the table with some values that would match each constraint. And when you've got your head wrapped around what those look like, let's go ahead into Desmos and put these two equations in there so we can solve this system of equations by graphing. If both of these situations are true at the same time, we can figure out by making a graph what's the only combination of X and Y that meets both solutions at the same time. So let's go over to Desmos. Okay, and I'll get rid of these. So let's start with X plus Y must equal 16. I think it was 16, right? Yeah, 16 tickets. And then the total price is 141. So 1050 X plus 750 Y equals 141. Okay, again, two lines. The green one represents all the possible number of tickets that add up to a total of 16 tickets. And the purple line represents all the possible ways you can add those tickets together, and it's $141. And there's only one solution to it that matches both constraints. That is 7 adult tickets, 9 child tickets. 7 plus 9 does equal 16. And if I do 7 times 1050, I believe it, I'm just checking. 7 times 10.5 is 73.5. And then 750 times 9 is 67.5. So adding those two up together will get you $141. Okay, the last problem. So we'll go down here, poster shop. Han paid $16.50 for 2 large posters and 3 small posters of his favorite band. That's a lot of posters to buy at one time of one band. Han's a super fan. Kieran paid $14.15 for 1 large poster and 4 small posters of his favorite TV shows. Posters of the same size have the same price. So there's a there are prices of large posters and there's prices of small posters. Now in this situation, the constraints are a little more complicated, but still doable. If we buy 2 large posters, so 2 times X, and we buy 3 small posters, so 3 times Y, then we get 1680. And if we buy 1 large poster, so 1X, that's supposed to be an X, not a Y, that's an X, plus 4 small posters, so 4Y, and we add those up, then we get 1415. And my writing started to get terrible as I go through this, but there's my system of equations. You can fill in the table with values that would match for those situations, but at this point, I feel pretty good about just going ahead and graphing it and then seeing how that graph turns out. So let's go on over to the graph. Okay, and here we are at the place that we left off. So the graph of Han's poster buying is the black line, and that's all the possible numbers of posters that would add up to 1680. And then the red line is Kieran. That's all the possible numbers of posters that would add up to 1415. And once again, there's only one value that meets both. So the price of the large poster would be the X value. That's the one represented by X. That would be $4.95. And the price of the small poster is $2.30. That's the only price combination that matches both situations perfectly. So now we know how much those posters cost, and we can problem solve through it by solving a system of equations. Your assignment is to do some systems of equations practice on Khan Academy. So on Khan Academy, they'll show you a system of equations marked with a little curly brace. And You can use their little graphing tools to graph those equations and then find out where they cross. It's also perfectly acceptable to plug those two equations into Desmos, find the place where those lines cross, and then you can choose the correct choice that represents the solution to that system. All right, good luck, and I hope you enjoy the task, and I'll see you next time.